Good afternoon. This is Bingson. Today I'm going to present the power of data-oriented attacks by passing memory mitigation using data-only exploitation technique. Actually, this is a part 2 of our data-only attack series. The part 1 has been presented by my colleagues in Black Hat Asia about 2 weeks ago. I'm not sure if you guys have got a chance to check my slides. In part 2, we're going to present some more interesting examples to further illustrate the data-only attack. A little bit about me and my co-presenter, Chong. I am the senior security researcher, and I'm leading the IPS security research team of McAfee. We used to be Intel, security group of just, spinned off. Okay. Chong is the senior director of McAfee Labs IPS team. Due to some urgent issue, today he cannot make it to speak with me. Now we're gonna skip abstract. The agenda. First of all, I will start with introducing some background information about CFG and CFG bypass, which include corrupt functions, return address on stack, transit via unguarded trampoline code, call function out of context. Then we'll use a pretty complex example to illustrate one of the commonly used CFG bypass method, call function out of context. And next comes the highlight part of this talk, the data-only attack. In this section, we'll present to you 2 interesting examples of pure data-oriented attack. Actually, in part 1, we demonstrate how to load the disabled Silverlight plugin on Microsoft Edge. That one is pretty simple, just require flipping 2 flag bits. And this time, in part 2, we'll see some more complicated data-only attack techniques. And at the end of this talk, we're gonna provide some suggestions for preventing data-only attacks. And we're gonna draw a conclusion. Yeah, this is pretty much outline of this talk. Let's get to the details. CFG, the control flow guard, is a compiler-aided exploitation mitigation mechanism that prevents exploit from hijacking the control flow. I think many people already talk about how CFG works, so here I won't waste time to repeat. One thing I want to one thing I want to mention is the dispatch mode, which was introduced on 64-bit system. And the difference between the dispatch mode and the check mode is check mode's logic is check and the return, right? And the dispatch mode is check and the call. Now I'm using this diagram to illustrate how dispatch mode CFG works. For a memory indirect call in dispatch mode, as you can see, there will be only one call, right? Because the actual function call will occur inside the CFG validation routine. So there will be only one call. In check mode, you will see 2 calls. What happens inside the CFG validation routine is, first, the high 55-bit of the call target address will be used as the index into CFG bitmap to retrieve a 64-bit bit map entry. And then the bit 3 to 8 will be used as an offset. and then it's gonna test the bit offset of that bit map entry. If that particular bit is set, that means the target address is valid. So in the end, it's gonna jump to that target address. As you can see, in the end, jump RAX. Otherwise, if that bit is not set, that means the target address is invalid. So it triggers an exception. Here are some major CFG bypass methods. It may not be a complete list. First, bypassing CFG through return address corruption. This is a known limitation of CFG. So it was commonly used in those hiking contests or as well as some real-world attack scenarios. This bypass relies on knowing where the stack locates. Later, we'll be showing such an example of leaking the stack address using the data-only technique. Nowadays, the vendor had been trying to develop some mitigation features to solve this problem. For example, a Microsoft RFG, the return flow guard, the Intel CET. Speaking of RFG, here is an interesting episode. Actually, after this feature was added into the Windows 10 Insider Preview build, we did some research, hope to find some, figure out a way to bypass it. However, later we were surprised to see this feature was soon taken out from the Insider Preview build. At that time, we really suspect there must be some issue, must be some defect with this feature. And then later, our suspicion was proved in the Kansas West last month. The Microsoft guys admit in their talk, the RFG has some design level defect that allows for a bypass. So this feature was pulled and became an experimental project. So far, we haven't got any detail about this bypass. Transit via unguarded trampoline code. This kind of issue is mostly about taking advantages of an unenlightened JIT engine, such as the JavaScript engine, the WAP, WARP. However, as JIT security improves, such kind of issue has declined. The last category is call function out of context. Next, we'll be discussing this technique in details and show one interesting example. Now we'll explain what is out of context function call and how to make such a call. The basic idea of calling a function out of context is to issue a function call to certain unexpected target address through memory indirect call instruction. The reason we call it out of context is because from the program's logic perspective, such a call is not supposed to happen from that call site. For example, let's say we replace a function pointer in an object's VF table with certain API, so that we can call that particular API through the object's method. Although this doesn't have any problem from the instruction execution's perspective, however, it does violate the program's original intention, because the object's method call instruction should only be used to call into the object's method rather than arbitrary API, right? How to make an out-of-context call? First, we need to override an existing function pointer. And then we're going to trigger the overwritten function from the context of a scripting language. In order to make this happen, there are a few conditions need to be met. First, the target function address need to be able to pass the CFG check. Second, the number and order of arguments to the target function should be controllable to the scripting language. Third, sometimes it's preferable to get the return value back in its original form. Here is a good example of a calling function out of context, which is able to control all the arguments and get the return value back. Actually, I leveraged some of his work when creating my own demo code on 64-bit platform, especially the framework that used to achieve the AAR and AW on 64-bit. Now we already know what is out-of-context function call and how to make such a call. Next, we're going to show you how to leverage this delay load import mechanism to bypass CFG. Before we explain how to make an out-of-context function call to a native API of delay load, first we need to understand what is the delay load import mechanism. Interestingly, in this talk, we'll be introducing two OS internal mechanisms. One is this delay load import, and the other is LdrpWork, we'll be introducing later. And both of them are related to the OS module loader. The delay load import is a mechanism that enables the fast loading of a module by allowing its imported DLL to be loaded only on the first call to a function in that DLL. Basically, it works like this. When the loading of imported DLL is delayed, the important function in that DLL will temporarily temporarily pointing to some stop function. And later, when the important function is called, its stop function gets called first, and it will use a helper function to actually load in the imported DLL and to resolve the imported function to its real entry point. And after that, the call to the important function can go naturally without the intervention of the stop function. And the helper function calls a native API, the ntdel resolve delay loaded API, to do the actual job. And a critical data structure delay import descriptor will be passed to this native API to instruct it how to perform the delay load import. Let me use that example to make it more clear for you about this mechanism. In this case, as you can see, when inet imports bcrypt.dll, that is delay loaded. Therefore, the important API bcrypt.gen_random is temporarily pointing to a stop function, the load _ bcrypt.gen_random something. When this API is first called, this stop function gets called first, and it jumps to some intermediate function, tail merge, blah, blah, blah. And this intermediate function will call a helper function, delay load helper2, to perform the actual delay load import. As we mentioned before, the helper function will call a native API resolve delay loaded API to do the actual job, but this is not shown in this screenshot. After the delay load import completes, the imported DL bcrypt will be loaded, and then the imported API bcrypt gen random will be resolved to its real entry point. And here, the function pointer replacement occurs inside this native API, the resolve delay loaded API. Yeah, from the previous explanation, now we know the native API resolve delay loaded API can be leveraged to overwrite a read-only function pointer. Actually, there's another API called resolve delay loads from DL that can achieve the same goal. But in terms of making an out-of-context call, the latter, the loads from DL one, it's much easier to call because it has fewer arguments to control. The first one, I think, if I remember correctly, has 6 arguments, and this one has 3. So in terms of out-of-context call, this one is much easier. The concrete bypass scheme is something like this. First, we're gonna fake a PE, create a fake PE in memory, and this PE carries a malformed delay import descriptor. And there is a field called import address table RVA in this malformed descriptor. This field points to the function pointer we want to overwrite. And this could be outside the fake P. Later, we're going to show a diagram. It's a little bit complicated, you know. And then we're going to fit this fake P to this native API, the LDR resolve delay loads from DL. In addition, in order for the operating system to believe our fake P is a loaded module, we need to corrupt some existing entry in system's loader data table. And also, the size of image field of the corrupted entry need to be set big enough to pass some range check inside this native API. Now, this diagram can help us get a high-level understanding about what happens, you know. The blue rectangle is our fake P created in memory. It has a malformed descriptor, delay load descriptor inside it. And in this descriptor, the import name table RVA is referring to an exported API in ntdel. While another field called import address table RVA is pointing to the import table of chakra. The reason we call it the malform is because, as you can see, the import address table is actually outside the fake P itself. And in this case, it is in the chakra.dl. And this particular descriptor actually requests the OS module loader to replace the current function pointer in gotcheck icon FPTR with the export function in ntdel. That is the ntcurrent TB. Besides, in order for the operating system module loader to believe our fake P is a loaded module, we need to either corrupt, you know, an existing entry in LDR data table, or we can just to create a new one. And the DL base is pointing to the base of our fake PE. And the size of image is set to 2G. It's big enough to pass the range check. By the way, the loader data table can easily be located as long as you know the base address of NTDEL. And it's not protected from write. So you can, insert a new entry, or you can modify existing entry, whatever. The following pages are actually giving the details of this CFG bypass. However, due to the time constraint, I won't be able to do a deep dive. Instead, we'll be quickly, working through these pages. For this example, it makes out of context function call by replacing the function pointer of JavaScript array entry push method. And this is the original call stack of this array.push method. And this page shows the call to this method is redirected to LDR resolve delay loads from DLL. And as you can see, all three arguments are passed in correctly from the JavaScript. The first argument is the fake PE. The second is the DL name, and the third one is 0, as we expected. These are some disassembler code, so I won't, talk about. You guys can read my comments. Yeah, here is the range check we previously mentioned. The range check. This screenshot shows the corrupted LDR data table entry and how it is leveraged to pass the range check. As you can see, the DL base is pointing to the fake P, and the size of image is set to the maximum size of a module. In this case, I set it to 2G. This screenshot shows the malform, the descriptor. As you can see, the import name table RVA is referring to an exported function in NTDEL. It's ntCurrentTB. It's basically a blank function. And the import address table RVA is pointing to the import table of a chakra, which is outside the fake P. This is where the actual function pointer replacement eventually occurs, as you can see. Override the function pointer. In this internal function, LDRP write back protected delay load. Now this is the outcome of this CFG bypass. The chakra got check ICAL at PTR has been replaced with unprotected, which is basically a blank function. So at this point, the CFG check for chakra, was completely removed. No CFG check enforced on chakra.dl. One thing to be noted is, as you can see, the memory attribute of chakra's import table is still read-only. So this attack can only be used to replace a read-only function pointer, but not to make arbitrary read-only memory writable. Now let me show you a live demo for this CFG bypass. We're going to use a WinDBG script to emulate AAR and AW primitives, because we don't, we're not using a real vulnerability. Okay, we use this command to, modify some JavaScript array to create the ability of arbitrary address access. Okay, now it shows, go check the replace the guard check icon FPDR. So let's check it out. Yeah, as you can see, the CFG validation routine has been replaced with some kind of blank function. This function do nothing, just return. So at this point, no CFG is enforced on tracker. You may notice the member attribute is still read-only. Okay, let's move on. According to my test, this CFG bypass works fine on Windows inside the pre-built 14686 something. However, on subsequent versions like 15048, this native API became invalid call target, so it can no longer pass the CFG check. In fact, calling function out of context has been explicitly marked as out of scope in the rules of Microsoft mitigation bypass bug bounty. Obviously, Microsoft is pretty confident that the fine-grained CFG implementation would be able to defeat all these kind of control flow hijacking, including calling function out of context. So the question now is, are we still able to bypass the memory mitigation without changing the control flow? The answer is yes, by using the data-only exploitation techniques that we'll be discussing next. Data-only attack, as its name suggests, it aims at manipulating the program's critical data but without diverting its execution control. And changing in programs data may lead to the change of the program's default behaviors. So it can be leveraged to achieve some powerful things, such as bypassing certain restriction and or some protection. Here are some example of successful data-oriented attack. The vital point extract that enables JavaScript God mode by just flipping one bit in an object. Also this one, Microsoft EMAD bypass by tampering with its configuration data in memory. What kind of data will be targeted? Theoretically, any data that can be leveraged to change the program's default behavior will be targeted, such as certain global variables in the data section or some critical flag in an object. And this data could exist in the unprotected data section, heap, private data, or stack, and so on. How to perform data-only attack? There are some key factors that are very crucial to a successful data-only attack, such as the ability of arbitrary address read and write, and being able to accurately locate the target data at runtime. And sometimes the existence of certain data is transient and time sensitive, so the timing may play an important role in these cases. For example, if you want to modify the data on stack, such as the local variables. With the concept of data-only attack in mind, now we'll see how to leverage the LdrpWork mechanism to launch data-only attack to bypass memory mitigation. First, I will introduce LdrpWork mechanism. Then I'll explain how to leverage this particular mechanism to first leak the stack address, and second, to bypass CFG. LdrpWork is an internal mechanism of OS module loader, and it is responsible for performing various loader-related tasks. And this works can be processed either synchronously or asynchronously. And asynchronous mode is specifically used to support the so-called parallel loading of the dependent modules. The in-memory structure of LdrpWork contains a fixed size header and the variable length part, the module name. We're going to show you a diagram. And in asynchronous mode, all the LdrpWork instances are organized in a doubly linked list, which is FIFO. The LdrpWork mechanism actually consists of 4 major functions. And the snapping is one of the important LdrpWorks, and it's fulfilled by LDRP snap module. Next, we're going to look at this function one by one. LDRP allocates placeholder. This function allocates a new work from the loader's private heap. LDRPQ work. This function inserts a new work at the tail of the doubly linked list. And both the head of the tail of this list are, the global variables of ntdel. So you can easily locate this, a doubly linked list. In contrast to the previous function, this function, join work queue, removes the head node and send it to the process routine. And the process routine is LdrP process work at the bottom, as you can see. LdrP process work process one single work, such as the work of module mapping or module snapping. And this function can be called in both synchronous or asynchronous mode. This is the process for module mapping, as you can see. We mentioned the snapping as one of the most important works supported by this mechanism. And the LdrP snap module process the work of snapping. Snapping means loading the dependent module and resolve the imported functions. At the end of this function, as you can see, it calls an external function do post snap work to restore the iData section memory attribute. Do post the snap work, restore the memory attribute of iData section, and also known as import table, to its original setting in PE file. Also, this function responsible for making sure those critical security check functions are correctly resolved, such as the guard check ICALL FPTR and the guard SS verify failure. A loader work of snapping should look something like this in memory. It starts with a fixed size header, which includes the Unicode string of module name, the loader data table entry of current module and its parent module, and the list entry, and followed by the information about dependent module. Also, the information about the iData section, including start address, memory attribute, and the size. The size of the header is hex B0, and it is followed by a variable length part, which stores the Unicode module name. As you can see at the bottom, duser.dl. This screenshot shows the data structure of LDR data table entry. At offset hex 98, there is a data pointer pointing to another structure called LDR DDAG node. At offset hex 38 of this structure, there is a field called state. And the function LdrP process work will determine what kind of work to take to process according to the value in this field. In this case, the state is 4, which stands for LDR module snapping. So up to this point, you should have a basic understanding of this loader work mechanism. So now it's time to explain how to leverage this mechanism to, do some real attacks. If you look at the offset hex 10 and 20 of this loader work instance, as highlighted in red, you will see some interesting value there, right? And it turns out these values are stack address. And they belong to the thread on which the loading of a module operates. Now the question comes, is it possible for us to leak those stack address from the LdrpWork structure? The answer is yes. However, there are some obstacles we need to overcome. First, the LdrpWork structure stay in the queue only for a very short time period. It will soon be removed for processing from the queue. So it's really hard for us to trace it by reading it from the queue. This is time sensitive, as I mentioned before. Second, the size of the LdrpWork structure is variable due to the length, the difference in the length of the module name. So we're not able to accurately predict its location in the heap. Eventually, after some in-depth research, I figure out a way to accurately, locate such a LdrpWork structure in memory and leak the stack address out of it. And knowing the address of a stack will be, able, easily bypass the CFG by corrupting a return address on it. Now let me show you this stack leaking attack through a live demo. We'll use this command to emulate arbitrary address read and write. And we need to wait for a while. Okay, it shows a LdrpWork is located at this address, and the stack address is leaked is 9A92 blah 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 blah. Now let's use the WinDBG to verify it. Nine eight nine two DF. We're gonna search. Okay. Yeah, this is the thread the stack address belongs to. See? the stack address we leaked is in this range, right? Stack limit and stack base. Okay. Yeah, let's continue our presentation. Yeah, addition to the stack address leaking, the LdrpWork mechanism can also be abused to make arbitrary read-only memory writable. DAOs to bypass CFG. This is possible because first, there's no protection on LdrpWork's doubly linked list to prevent it from being, modified. Second, the loader module snapping work can be leveraged to change the memory attribute of arbitrary address. The whole exploitation process is something like this. First, we're gonna fake a LdrpWork structure in memory, and this LdrpWork carries all the information needed for the memory attribute change. And then we're gonna insert it to the system's the work queue and waited for it to be processed. That's it. Very simple. Yeah, this is a diagram of this CFG bypass scheme. The blue object stands for the fake LdrpWork that we created in memory. And as you can see, the address of iData section points to the import table of chakra.dll. And the attribute we specified is page read and write. So this LdrpWork actually requests the OS module loader to change the memory attribute of chakra's import table to the one we specify in this case, page read write. Yeah, in order for this fake LdrpWork to be picked up by the OS, we'll have to insert it into the LdrpWork queue that is maintained by the OS, but no protection. Yeah, insert it. The memory attribute change occurs in this internal function, do post snap work. In this case, in this particular POC, we choose to change the memory attribute of our chakra's import table. And this address is, specified in the LdrpWork structure. Similar to our first demo, the outcome, is the guard check icon, FPTR, has been replaced with some blank function, in this case, ntdel RTL get current PEB. It does nothing, just a return, right? And the import table of chakra, the memory attribute of the import table of chakra has been changed to page read and write. Solution for CFG bypass abusing LdrpWork. Actually, for this particular case, it can easily be fixed by enforcing a check on the target address to make sure it indeed belongs to the iData section of some module which is in the snapping state. However, Microsoft consider corrupting a mutable read-only memory is a no limitation. So they know there could be a variety of methods which can be used to subvert the read-only memory. So instead of adding the point fix for each possible method. They're looking to address it in a more generic way. Yeah. Maybe they're gonna move, like the ACG, they're gonna move it out of the sandbox process. So far, we have been shown the power of a data-only attack through a couple of examples. Then how can we prevent such data-only attack? Basically, there are two options to take. One is to protect your critical data. You can either apply the right protection on your critical data page, or you can use certain forms of encryption or obfuscation to hide the address of your critical data. Another option is always try verifying the integrity of your critical data before using it. With extra logic, many such attack can be prevented in their early stage. Yeah, at this point, we're pretty much done with our talk. Here are some takeaways. First, the fine-grained CFI solution will eventually defeat all kinds of, control flow hijacking, including the one we talked about, the calling function out of context. Second, today there are still lots of unprotected data. They can be leveraged to conduct data-only attack. Third, data-only attack is difficult to prevent. Also, as the awareness being raised about the danger of the data-only attack, the battle has now escalated to, the condenting of read-only. The protected memory. There are not much low-hanging fruit, Last, data-only attack may have some variations, and it can be combined with some other exploitation techniques, such as the race condition. Yeah, this concludes our talk of data-only attack. We'll be covering some more advanced data-only attack in our future conference, so stay tuned. If you have any question, you can send your question to our email. And here we would like to thank MSRC for getting the issue we reported fixed in a timely manner. And also we want to thank our colleagues for their helps to our research. Okay, that's it. Any question? So I can take question offline if you want. I'll wait here. Or
did I understand correctly that you were suggesting validating in-memory structures to make sure that they're not being corrupted by these attacks?
Sorry, you mean this slide? It's a suggestion?
Right. Yeah, you're suggesting like doing some sort of authentication of the in-memory data prior to each use to make sure that it's not being corrupted. Would it not be possible to just forge the authentication as well? Or is that presumed too challenging?
Yeah, I think sometimes it's going to affect the performance, so it's not, suitable to do such kind of, checking or verification, on each place. Yeah.
I mean, if you put performance aside as a radical solution, couldn't you put the loader data structures into kernels so that you say, okay, if I want to put something in the loader list, this is a kernel call. The kernel maintains the loader list, and at some point loads the module and places it into your user data space. Because then, without being in kernel mode, you couldn't manipulate the data structures anymore. But you would have the context change for every load. I mean, this could be a solution. Probably kills you off with performance.
Yeah, but we cannot move everything into kernel mode, right? Yeah, because we have discovered some interesting bugs by breaking some frequently used data, such as some synchronization logs, something like this. You cannot move, all this, stuff into the kernel space, right? So, I think right now Microsoft is still working on it, trying to resolve these issues in a generic way. Let's, look forward to seeing their solution.
So you mentioned just now locks as an interesting target for manipulating. What are some other interesting categories of data to attack that will result in bugs? Because I haven't had a chance to think about what you would actually pop.
We can talk this offline, because we'll be covering this in our future conference.
Great. Any more questions? Well, thank you. Let's thank Bing Soon for his presentation.